our rigid body, except that now there's rotation, and before we can do anything with rotations, we need to find the counterpart analogous to mass, which is called inertia, moment of inertia. So this lecture is about figuring out moment of inertia for certain geometries, and that knowledge will be used later on when we use F equals ma for rigid bodies. So this is a section on moment of inertia. So I will give an overview of formulas you need to know in order to find the moment of inertia, and there's something else which is called the center of mass, and then we will solve problems. So center of the center of mass is the location at which you can assume that all the mass of the body is concentrated. The formula for that is x bar is summation mi xi divided by summation mi, and y bar is mi yi summation mi. Okay, I think it's best to illustrate this through an example, but here is what I mean by center of mass. So if you consider two rectangular plates, okay, you know that the center of mass for the first place is right at the middle, so that's going to be x1 y1, assuming that this is the origin. So this is x and this is y, and the center of the geometric center of the second one is going to be the location of center of mass for the other rectangular plate. So this is x2 and y2. So what we're trying to do in this formula is we're trying to find where exactly is the center of mass of the combined system of G1, G2, and that will be somewhere here. Okay, again, I'm just putting it there. It really depends on the mass of the two and so on. But let's say that's over here in this position. G has coordinates of x bar, which I wrote down there, and y bar. Okay, so if you want to find that, you got to use these two formulas. Okay, so that's the first thing. The second thing is called moment of inertia. The moment of inertia is defined as it's called I, and I is r square dm. So how do you compute it? Well, if you have a rigid body, and let's say that it's rotating about this axis, then you're going to take a element of mass dm at a radius r and take this integral across the whole mass of the body. If you did, you probably came in calculus when you were doing double integrals, triple integrals, you were computing moment of inertia, right? You're not expected to know double and triple integrals, but you are expected to know some of the formulas, which I'm going to show you in a bit. Okay, so this is actually a prereq calculus. Need to use double and triple integral. Okay, so again, we are not expecting you to know double and triple integrals. What you would have done if you had taken, if you have done double and triple integral, is you would have computed the inertia for some geometries. Okay, here are 8 such geometries which are important. Okay, sphere, hemisphere, disc, ring, cylinder, cone, rectangle, and then also a cylinder. Slender rod, but that's a cylinder. Okay, so you're not expected to remember this. We'll give you the formulas. Only some of these are actually important, which will come again and again in this class. The ones which are important are, so I'll abbreviate that with a star. So these ones come again and again. Thin circular disc, thin ring, thin plate, slender rod, and cylinder. Okay, if you notice this, let's look at one of these. Let's say the thin plate. Okay, you see there are 3 formulas: this Ixx, Iyy, Izz. What does that mean is Ixx is the inertia about this axis. So when you rotate this when the plate rotates about the x-axis, that's the inertia you're going to use. So if it's, for example, pinned here and it rotates this way, then you would use that. If it's rotated about the y-axis, you use the second formula. If it's rotated about the z-axis, like this, then you would use the third formula. So you got to know this. Unless you know this, you know the direction rotation, you cannot use it. So don't arbitrarily use any of these formulas. So see that they're different. Okay, so before we start solving problems, there's another important thing, and this is kind of crucial. It'll make your life easy. Is this theorem called the parallel axis theorem? Okay, this is what the theorem says. So I'm going to assume that the center of mass is G. Okay. So we know the inertia about G. Where does that come from? Well, it comes from that table which I just showed you. Sometimes this particular body rotates about a different axis. Let me call this ZG. Let me call this axis ZO. So the inertia about an axis parallel to the previous axis is what is asked, what you got to find. And you want to do that because the rigid body does not rotate about IG, it rotates about, or ZG, it rotates about ZO. So in this case, you can find relation between IO, IG, mass, and this distance D. So here, an important thing here is ZG and ZO are parallel. Okay, the parallel axis theorem says that inertia about a different axis, about a parallel axis, is inertia about the center of mass plus the mass of the body times the distance squared. It's the distance between the 2 axes. Okay, example would be, if you're given a double pendulum or a single pendulum, sorry, this is IG, this axis, this is IG axis or ZG, okay, this is ZO. So you can use the formula for IG, the mass, the distance between the Z0 and ZG axis, to find the inertia about the axis about which this pendulum is rotating. So it's rotating like that. Okay, so final thing, is radius of gyration. Okay, sometimes instead of giving you that table which I showed you some time back, we just give you a radius of gyration. So if you're given the radius of gyration, which is denoted by k, then inertia is simply mass times k square. So if you're given the radius of gyration, that is the inertia about the center of mass. Okay, it's always about the center of mass. Okay, let's use all this to solve some problems. Okay, determine the moment of inertia about an axis perpendicular to the page and passing through the pin O. So means that the axis, it's really hard for me to draw this because the axis passes through this. Okay? When the axis passes through O and through the perpendicular to the page, means that the plate with the hole will rotate this way, right? Or I can draw it this way if you're, that's Z0. The thin plate has a hole in its center. Its thickness is 50 millimeters and the density is 50 kg per meter cube. Okay, so if there was no hole, if it was a fully covered square plate, then, and if you're told to find inertia about O, then clearly you would first find inertia about G, because that's the center, and then use the parallel axis theorem to find inertia about O, right? The trick is here to do the same thing, but find the inertia of the square plate without the hole, find the inertia of the hole separately, assuming that there was mass in that hole, and then you subtract the two to get the inertia. So here is how you can do it. Okay, that's the question. Find the inertia about O. We'll break this up into two parts. We'll find the inertia about O for the square plate. I'll call that 1. We'll find the inertia for a hole, well, not really a hole, a circular plate with the same density, same thickness, about point O. So I'll call that 2. I'll take IO1 minus IO2, and this is going to be my answer. So all I need to do is now find IO1 and IO2. The reason I broke it down to this fashion is because the table gives me formulas for those two geometries. Okay, so let's try to find IO1 from table. So from the table, we'll find IO1 equals. So the first one is a square plate The table doesn't have a square plate, it has a thin plate where it's really a rectangle. So let's try to find where that is in the table. Okay, so it is a thin plate, what we're after. Okay, which one should I use? Should I use XX, YY, or ZZ to find the inertia about the center of mass? Z, right? Because plate is like this. You got to find the axes which are normal to the plate, and the axes which are normal to the plate is the z-axis. So we got to use this formula. So it's 112 mass times a square plus b square, but a is equal to b, right? It's square plate. So it's going to be 2a squared divided by 12. So it's m a squared divided by 6. So 1/6 times mass times 1.4 square. Now what, let me just write it this way. Okay, the mass is, what's the mass? It's the density times the volume. The volume is the area times the thickness. So 1.4 times 1.4 times the thickness, which is 50 mm. So 50 divided by 1000. Okay, so that gives me the inertia about the center of mass, or this point. I need to find the inertia about, oh, right. So for that, I need to find the use the parallel axis theorem. So it's going to be Ig plus mass times the distance from G to O. So G to O. I need to find this distance. So what's that distance? Yeah, so this is 1.4. So if that is 1.4, that's 1.4, then the diagonal is going to be 1.4 square plus 1.4 square by Pythagoras theorem. But it's going to be half of that. So it's going to be, I believe, 0.7. So it's half of 1.4 square plus 1.4 square, which is 0.7 square root 2. So this is 0.7 square root 2 square. The mass is again given with the same formula. Okay, so doing the math here gives me 6.4 kg meter square. Okay, then I need to find inertia of the sphere, sorry, the disk about an axis passing through O. So again, I need to go to the table. Okay, this is a thin circular plate which I'm after. I need to find the inertia about Z, right? Because it's going to spin about an axis perpendicular to the plate. So it's IZZ, which is what I'm after. It's half m times r, or radius squared. So going back to this, half. We call this M1 to distinguish from the other geometry. So half M2, the radius is 150, so 0.15 square. Okay, but that's the inertia about the center of mass, or G, or G2. This is about G2. I need to use the parallel axis theorem to find the inertia about O. So that's going to be mass times the distance from G to O, which is the same as the previous one, 0.7 square root 2 square. So M2 is the density times the area, which is pi times r square, times the thickness, which is 50 divided by 1000. Okay, plugging in these values, so everything is known here, right? So the plugging in the values gives me 0.175. So IO12 is 6.4, which is the inertia of the square plate without the hole, minus the inertia of the hole, but with the hole filled with mass of the same density. So that is 6.23 kg meter square. Okay, there is actually another way to do this problem, and I will set up the problem, but I want you to do it later on yourself and see if you get the same answer. Okay, the alternate method is as follows. So you take the geometry you're looking at, you find the inertia about G1, subtract it from the inertia G2, so IG12 is IG1 minus IG2. Okay, once you do that, that's step number one. The second step is you found the inertia about IG12 is known. Now, in order to find IO12, you do IG12 plus the mass of the system, which will be the mass of the square plate minus that of the hole, times the distance squared. This is so mass of, maybe better way to write this is m1 minus m2 d squared, right? And check with previous method. Okay, I'm just going to give you some hints. So IG12 comes out to be 1.5987, and so this is an intermediate. So see that you get that answer, and then you should plug in the value here, find this, and so that IO12 is the same as what you get over there, 6.23. Okay, so you notice the difference in one question. In one way to solve this is to find the inertia about the axis O for individual bodies and then subtract them. Okay, it's one step. So use the parallel axis theorem individually. Then use it here, use it here. In the second case, what you do is you find the inertia about G first. And the second step is use the parallel axis theorem. So the first case you use parallel axis theorem in conjunction both times, but here you use it only once. Should give you the same answer. Any questions on that? So this is important because it's a precursor to doing rigid body dynamics, which we'll be doing soon.